In April 2026, a team at Berkeley pointed an automated agent at 8 of the benchmarks this entire industry quotes. 5 of them returned a flat 100%. A 6th came within rounding. It did not solve a single task. It did not get smarter. It went after the harness. 0 tasks solved. The work comes from Berkeley's Center for Responsible, Decentralized Intelligence. In the paper, Hao Wang, Hanxin Li, Xiuyang Meng, Alvin Chung, Kaushik Sun, and Don Song build an automated scanning agent and run it at benchmarks covering software engineering, web navigation, desktop computing, and terminal operations. Terminal Bench, 89 tasks, 100%. SWE Bench Verified, 500 tasks, 100%. SWE Bench Pro, 731, 100%. Web Arena, 812 tasks, approximately 100, not a flat one. Field Work Arena, 890, 100. CAR Bench, 100 on the hallucination set. GIA came in at about 98%. And then OS World, 369 tasks, at 73. 73 is not 100, and I am not going to round it up. 5 benchmarks returned a flat 100. Web Arena came within rounding. GI got close. OS World held up better than any of them. The argument does not need the exaggeration, so it is not getting one. Across the audited set, that is 4,458 tasks, and a scoring agent that solved none of them. The agent has a shell. To see why this happened, you have to see how an agent benchmark differs from the benchmarks that came before it. A question answering benchmark hands the model a string and compares a string. The model never touches the machinery that scores it. There is nothing to attack. An agent benchmark hands the agent a shell, a file system, usually a browser, and a task that runs hundreds of steps. Then it grades that work with code sitting in the same environment. The grader is a file on a disk the agent has been writing to. The paper's own framing is that reward hacking, where an agent maximizes a score without performing the intended task, emerges spontaneously in frontier models without overfitting. Their conclusion follows directly. Benchmarks must be secure by design. 8 ways to not do the work. The team compiled the failures into 8 vulnerability classes. The first 4 are about access. No isolation. Answers shipped with the test. Unsafe eval. Unsanitized judges. The second 4 are about rigor. Weak string matching. Gaps in the evaluation logic. Trusting the output of untrusted code. And granting permissions the task never needed. Across the benchmarks they audited, those 8 classes accounted for 219 distinct flaws. The tool that found them is called BenchJack, open source under Apache 2.0. 1 note on scope, the paper runs it against 10 benchmarks. The 8 I am showing are the ones the write-up details. We come back to BenchJack because the interesting part is not what it breaks. 4 of them in detail. Start with SWE Bench Verified, 500 tasks, the benchmark that defined AI coding progress for 2 years. The exploit is 1 file. The agent drops a conftest.py using PyTest's hook wrapper mechanism. The hook intercepts every test result during the call phase and rewrites it to passed. No bug is fixed. No code is repaired. Every one of the 500 tasks reports success because the thing asking the question was told to say yes. Field Work Arena is worse, and it is worse in a way that should make every engineer wince. Its validation checks exactly one thing. Did the last message come from the assistant? The function that would compare the actual answer is, in the author's words, imported but never called. It is dead code. So the winning submission for 890 tasks is an empty object. 2 characters. Terminal Bench takes a different route. During the agent's turn, the exploit replaces the curl binary with a wrapper. Later the verifier runs curl piped into shell to install its own tooling, and the wrapper is waiting for it. And CAR Bench is graded by a language model, so the agent simply talks to the judge. It appends a hidden comment asserting that all policies were followed. The authors are careful about one thing, and it belongs here. They state plainly that they are not claiming current leaderboard leaders are cheating. This was a scanning agent purpose-built to hunt exploits, not a shipped model caught in the act. Their claim is narrower and harder to dismiss. This behavior emerges without anyone training for it. That is why they say benchmarks must be secure by design. The vault door. Here is the part that decides whether any of this mattered. What happened next? On the 6th of May 2026, 1 month after the Berkeley post, Terminal Bench shipped version 2.1. It fixed 28 of its 89 tasks. Read what those 28 were. 9 where external dependencies had drifted. 8 where the resource budget was too small. The rest misspecified. Every one of those is a correctness bug. Real work, worth doing. And not one of them is the flaw class that let an agent replace the curl binary and score 100%. The 2.1 release notes do not mention security, exploits, reward hacking, or the Berkeley work. Continuous validation appears once, in the subtitle, with nothing under it. What a real eval looks like. This is where the story turns, and it turns in a direction most of the coverage skipped. The authors published an agent eval checklist. Run the evaluation outside the agent's container. Never hand the agent reference answers. Never evaluate untrusted input as code. And treat anything the agent writes as data, never as instruction. And the single most portable line in the whole paper, which you can apply to your own evaluation this afternoon. Build an exploit agent that does everything except solve the task, and see what it scores. If a zero capability agent scores above baseline, your evaluation has a bug. Then they prove the point constructively. The same tool that breaks benchmarks patches them. Run it as a loop, propose exploits, apply fixes, repeat. 3 iterations took the hackable task ratio from near 100% to under 10 on 4 benchmarks. Web Arena and OS World went to 0. These benchmarks are fixable. The tool that fixes them is public, open source, and free. It had 42 stars on GitHub when I checked. 42 for the tool that audits how this entire industry picks its models. So, an agent returned a flat 100% on 5 benchmarks, and neared on 2 more, by attacking the grader instead of the task. The flaw is structural, the thing being tested and the thing doing the testing live on the same disk. The most visible public fix repaired dependency drift and resource budgets, and its release notes never mentioned the exploit class at all. And the fix exists, it works in 3 iterations, and almost nobody is using it. Next time a launch post leads with a benchmark number, the useful question is not how high it is. It is whether anyone tried to score it without doing the work. Sources are in the description, primary ones first. Follow at InferenceWire for what the AI headlines actually mean.